of the genetics of what's happening. Before we go there, let's take a peek at this. This is actually a ductal carcinoma from excised breast tissue. You can see how the white material, the lesion here in the middle, is causing the tissue around it to retract in. And under sort of gross observation or palpation, this would actually be stony hard, right? It feel like a little stone within the tissue itself. As we move into what causes cancer in sort of the second half of today's lecture, we need to understand that there are a number of different things that can be mutagenic, that can cause mutations at the level of DNA and result in an altered replication or an altered replicative cycle of the cell. And this figure over here that I actually really like, it gives some examples of the different types of mutations that take place within cells, getting them closer and closer to becoming cancerous. So for example, if you have a mutation in the DNA that ignores normal growth cycles and you have this self-sufficiency, you're going to start replicating without any real signal. And that's indicated by this arrow. That's the arrow that shows where DNA replication begins in the promoter region. Remember that. This symbol right here is showing that there's an insensitivity of the tissue to anti-growth signals, signals that tell it to stop. And so the little symbol is, saying, no, I'm not listening to that. This little symbol right here says that there could be a mutation in the tissue's ability to invade other surrounding tissues and create metastases. And the way that they might do that is by upregulating the production of certain enzymes, like collagenase, so it can digest away the basement membrane of the tissue it's sitting in and move out. This symbol signifies that there's this sort of limitless replicative potential where it never stops. This symbol suggests that it can sustain new blood vessel development, because as the tissue mass enlarges, it's going to need new blood vessels to perfuse that new tissue to keep it alive. Remember early in the lecture I talked about how a lot of these masses have necrotic cores, so they have areas within them that aren't being perfused appropriately because they're growing faster than actually the blood vessels can develop. This symbol shows that it avoids cellular death, right? This little cross symbol. It's saying that it's avoiding mechanisms of apoptosis. There are definitely cases where you will recognize maybe a cell that's behaving inappropriately and you'll signal it for cellular death and you avoid cancer. But if there's a mutation in that cell to keep out of the view of apoptotic signals, then it will not be signaled to die. Now, typically, we're going to look at examples of many of these, right? And when you have cancer, most oftentimes you actually have to have mutations in two or more of these events or these capabilities within a tissue or a cell. So let me explain. If the cell that has the ability to generate lots of blood vessels, but it never grows, it's not going to become cancerous. Okay? It actually will result in what we call a hemangioma, which is a type of birthmark. Right? It's like a port wine stain that's underneath the skin that gets a little bit red because the blood vessels actually grow outside of the normal control pattern, but the tissue never grows with it. So it's just, and if you've ever known somebody, or if you have a reddish type of birthmark, and you went to see a dermatologist, and I'm wondering if this is, it's just a birthmark. It's nothing of concern. Because the only mutation that took place was abnormal blood vessel growth. That's it. So there's no worries. As long as it doesn't continue to change, then you don't need to do anything about it. You can have it laser removed, it's cosmetic, but that's why they're saying there's no problem. Or what happens is it has the ability to replicate out of control. And it grows this mass, and grows this mass, grows this mass, but it never develops any new blood vessels. Well, it's going to get to a certain size and just kind of stop. It's going to run out of nutrition. So you really, in order to be malignant in cancer, you really need multiple mutations. And that's the very top of the slide, talking about these multiple mutations. Well, in our body, we actually have specific types of genes, known as proto-oncogenes, that have an ability to be overexpressed. So they're highly susceptible to mutation, these proto-oncogenes. So a proto-oncogene is a normal gene that can become oncogenic or cancerous due to mutations or overexpression. And there are some that are kind of trigger points. Now, we're not going to look at all of them. We're going to talk about a couple, okay? And we're going to talk about sort of specifically some tumor suppressor genes. But these proto-oncogenes, if they're mutated, they can become cancerous, which is a word known as oncogenic, or an oncogene. And this autocrine capability is it can signal itself to continue to divide, which can be a problem. Now, how do these oncogenes come about? Well, if you look at this diagram, we've got three basic ways that we can actually mutate. Here is a particular chromosome, nothing of significance. We're just calling it a generic chromosome. Out of this chromosome, we're looking at a proto-oncogene. And you can see that there's a promoter region of where replication is going to start. Well, we could actually have a point mutation that takes place in our DNA that allows for that mutation to be expressed. The point mutation, or a single mutation, single base substitution would take place. And you have one nucleotide replaced with a different nucleotide in the genetic material. If we look at the next option, we can have what we call as gene amplification, where we get gene duplication. We get multiple copies of the gene taking place and produced. And so you get an overexpression of that trait or that phenotype. In the last example, we get this chromosomal translocation. And this is a chromosomal abnormality where you get a movement in a promoter region. So you get a promoter that moves to a spot where it's really not supposed to be, and then you get overexpression of that particular gene. So any one of these types of examples genetically could result in a proto-oncogene becoming oncogenic, where it's overexpressing what it's supposed to be expressing. Okay? If that oncogene codes for upregulation of cell proliferation, if that oncogene codes for an avoidance of apoptosis, and then in combination with that, new blood vessel development, we would see a mutation that's going to be favorable to that tissue to grow out of control and become metastatic. Okay? Now, the good news is in our body we actually have these genes known as tumor suppressor genes. These tumor suppressor genes do exactly like what the language suggests. They actually try to identify mutations that are taking place at the level of these genes, these proto-oncogenes becoming oncogenic. And they try to turn off the capability of that replication to continue. So in this picture, this is kind of a interesting way to represent it, but do you see this happy looking cell? Okay? It's like, is that supposed to be a smiley? Yeah, it is. Yeah. So this is, right, is like some fun eyebrows, and he's got like a probably a benign little squamous epithelial growth on his nose. But other than that, this is a normal cell, and this is actually looking at P53. P53 is a tumor suppressor gene. It's found in the body. We have a lot of them. We're going to talk about two in very great detail, or in significant detail, I would say. So a tumor suppressor gene is one that protects the cell on its pathway to cancer. And P53 has been identified as the central monitor of stress in the cell. So P53 expression right now in your body is upregulated during times of the day when you're exposed to different types of mutagens. So it's normally occurring. It's a tumor suppressor gene that's supposed to be on, and it's on when you actually see maybe tissue that's hypoxic, when you have radiation exposure, right? Like going outside on a sunny day. So we did a study in my lab, this is a clinical study, and we were looking at a topical therapeutic on the skin. And what we wanted to understand is, does it have any influence on P53 expression? Because we wanted to see if we could use it therapeutically to squelch skin cancer. So we actually found a study site in Southern California, and the inclusion criteria is we tried to recruit patients that had grown up in the area. So they had to have been there for 20 plus years, was the whole idea. And we specifically took biopsies from their left arm. Why their left arm? Because that's the arm that's sitting next to the driver's door, right? And in Southern California, a lot of windows are rolled down, or there's lots of sun for 20 years. So we took biopsies from the left arm and compared them intra-patient control to the right arm. One thing that we discovered was the right versus left arm levels of P53 were dramatically different. P53 expression in the left arm biopsy was orders of magnitude higher than the right arm. Okay? So P53 in these patients is upregulated because the UV radiation that you're seeing on the skin is causing cellular damage. And so P53 is there to find as the guardian of the genome, the central monitor of stress in the cell. Those are actually like street names for P53, like in the biz. You with me? It's like, hey, what's up? Central monitor of stress. Okay? The guardian of the genome. How would you like that? Like on your jersey? Guardian of the genome. Okay? I think that should be the name of the band. So you guys can borrow that if you like. Okay? Guardian of the genome. So P53 level goes up when sunlight is being damaging to the tissue, and these patients didn't have any skin cancer. They just had upregulation of P53. So P53 is protecting them from getting cancer. Okay, so let's see what P53 does. Well, what P53 does is when you have DNA damage, like with hypoxia. Hypoxia is one thing that triggers upregulation of P53. Another one is radiation exposure, ultraviolet radiation. P53 binds to the DNA. And then through sort of these two different pathways, right, through P21, you get a G1 arrest, right? G1 arrest, so that's gap 1 in the cell cycle. That's before mitosis. You guys with me? So if you pause in G1, you don't replicate the bad damaged DNA. In addition to that, it activates this molecule known as GAD45, and this causes DNA repair. So you pause replication, you repair the DNA, and then if you're successful, you allow replication to take place, and you get normal cells. You get normal onion-looking samples from your introductory bioplasms. Now, let's see what happens if P53 is altered, right? Sad face. The ionizing radiation, carcinogens or mutagens, cause DNA damage. You get no P53 activation, no cell cycle arrest, and you get all these angry-looking cells, and you get this malignant tumor. So P53, as the guardian of the genome, pauses replication through P21, and through GAD45, it allows for repair of the damaged DNA so that normal replication can take place. Now, if that doesn't work, if it fails, you can see that you activate what we know as the Bax gene, and this causes cellular death, and that has the ability to prevent you from getting cancer. So P53 is a great thing. It's a tumor suppressor gene. But if cells have a mutated P53, they're likely going to be cancerous. You with me? Let's look at a second one. So there's only 2 tumor suppressor genes that I'm going to talk about. There's a whole family, like VLA, APC, CD95, ST5, YPEL3, ST7, ST14. Right? So there's not just 2. But I'm just trying to expose you to 2, and those are the ones that we're going to cover in detail. This one's called retinoblastoma. Now, retinoblastoma is a different gene, a different molecule, but it has a very similar type of activity as P53. So, retinoblastoma exists normally in the body, and what it does is it sits down on the E2F site and causes a transcriptional block. So if you've got activation of retinoblastoma, right, it's going to sit in what we call this hypophosphorylated state. So the retinoblastoma is like this coat hanger looking structure here. Over here you can see how it opens up. See that? How it looks a little bit more like a coat hanger here. But in a underphosphorylated state, it sort of hugs E2F. And as it hugs E2F, this complete structure sits down on this E2F site and allows for histone methyltransferase as well as deacylase to form this complex, and this actually causes a transcription block. And now the cells are also arrested in GAP1, and it allows for DNA repair to take place. Well, when it wants to lift off, you add 4 more phosphates, hyperphosphorylation, so now there's 6, lift retinoblastoma up off of E2F. E2F still finds its site, but the complex doesn't form, and this allows for transcription to take place. So in a similar type of way, but a very different molecule using a different mechanism, retinoblastoma is a tumor suppressor gene. It was actually the first tumor suppressor gene that was actually discovered. So it's kind of a classic one. Now, let's go back to this idea of metastasis, and let's cover some of these mechanisms. So if you look at the stages of metastases, or breaking out, you've got a transformed cell up top, and here you have a metastatic tumor down below. So what takes place? Well, there's lots of intermediate steps that happen. First is that transformed cell has to find some avenue by which to move. So if it doesn't move out of its local area, it's never going to metastasize and create what we call a MET, right? A metastatic lesion somewhere else. So the way that it's going to get out is you've got this ability to mutate, break out of the basement membrane, releasing matrix metalloproteases to chew up this tissue, find its way into the bloodstream, float downstream to some other site, extravasate out because it can chew through this basement membrane again, and then set up a secondary metastatic location. Now, the way that it does this is shown here through the bloodstream. It could also be the lymphatics that it does this. It could also be by penetrating different body cavities. Right? So one thing that usually happens with patients that are long-term chronic smokers and develop lung cancer is that because the lung is extremely well vascularized and it's found within the thoracic cavity, it's very likely that either blood vessel, lymphatic, or other body cavities are going to be penetrated by the metastatic cancer, and it ends up going somewhere else, oftentimes to the liver. And the liver cancer is actually what takes the patient, because liver function is compromised, not necessarily lung cancer. So it's a lot of those secondary metastatic lesions that cause a lot of the long-term problems. Here's a question for you. See if you can, tonight, do this homework. Write this down. Record yourself, right? All of you have devices that can record your talking, okay? Call yourself. Leave yourself a voicemail. And then call back and listen to it, right? I want to see if you can describe the development of a malignant neoplasm, and you try to use normal, dysplastic, in situ, and invasive. And maybe things even like anaplasia. You could write these down if you want, if you just want to see in the class, just do this. But if you want to get a B, maybe add like anaplasia, pleomorphism, okay? And you really want an A, see if you can tie in there P53, okay? Or maybe proto-oncogene. This might be a good SI activity. Come loaded to see if you can actually practice this speech in front of your colleagues. Okay? If you don't practice these terminologies, it's like a foreign language within a foreign language, guys. Right? It's really tough to remember, especially for the upcoming exam. Now, as we continue on in the lecture, this is a secondary metastatic lesions that have actually targeted the liver. So all of these white spheres are all metastatic cancer that came from a patient that was primarily metastatic lung cancer. Now, in these tissues, where we've got these multiple mutations going on, we've got one of them that we called out, which was sustained angiogenesis. So one thing that we know that was discovered and popularized by a physician researcher named Judah Folkman. He was a cancer researcher. Ironically, he passed away from heart disease. Like I said, something's going to kill you, right? That's one thing for sure, is we're not going to all live forever. But Dr. Folkman was studying how to block cancer. And his idea, his thought was, well, if we starve the cancer, it won't continue to grow. So his research on anti-cancer therapy was all about anti-angiogenic drugs, giving cancer patients chemotherapy, a chemical therapy, that's what chemotherapy is. But these chemotherapy was actually targeted towards slowing down blood vessel development. Because what we know is that these lesions, right, here's the blood vessel, here's a blood vessel, here's a tumor, and the tumor is releasing different types of enzymes that chew away the tissue, allow a pathway for the blood vessels to get there, and they simultaneously release angiogenic growth factors like vascular endothelial growth factor. And that causes new blood vessel development to come to the tumor so that it can actually get more nutrition so it can grow bigger. Okay? It is kind of like a parasite within you, and it's growing out of control. Other chemotherapy agents, because students always ask about it, other chemotherapy agents, the very common modality of chemotherapy is using pharmaceuticals that target and kill fast replicating cells. And because they're fast replicating cells, we know they must be cancerous because they're growing quicker than normal, out of control, right? Quicker than what we would expect, and they're autonomous. Well, the side effects of chemotherapy can be vast, but some of the real challenging ones are there are other fast replicating cells that also die off, right? And the ones that line the gut, so a lot of nauseousness, a lot of ill feeling, a lot of diarrhea, a lot of intestinal side effects, pretty crummy kind of side effects, because these fast replicating targeted pharmaceuticals aren't specific enough to target just the cancer. Well, your hair follicles are also fast replicating cells. And so that's why a lot, not all chemotherapy drugs are that, but many of them that are pretty broad-based, those side effects, again, those are more aesthetic. But again, considering what the patient's going through, when you put all this together, it leads for a very difficult treatment regime. Okay, question?
No, never mind.
Yep. Okay. So, anti-angiogenesis therapy. Now, question for you, why would some cancer prevention researchers be looking into how shark cartilage develops and is maintained, to look at developing new anti-cancer research? Any ideas on how this relates? Cartilage. What do you know about cartilage?
Well, we know it's not highly vascularized, but I don't know why we do sharks instead of something else.
I don't know why we do sharks. It's cool. Like, what do you work on? Sharks? No, pretty badass. So I don't know why it's sharks, but it is because probably they have an awful lot of cartilage from a model standpoint. They're big organisms. But the cartilage is avascular. And so by understanding how the cartilage develops in these organisms, and it never developed beyond that, and keeping it avascular is one way to keep it cartilage. And so they're looking at mechanisms to continue on with Dr. Fulton's idea of, could I starve the disease? Could I starve the cancer from actually getting nutrition and therefore limit its ability to spread? Now, I want to talk about this concept of microevolution within the realm of cancer conversation. So this is sort of an interesting concept. Another term for it is called clonal proliferation. And the reason that I find it somewhat fascinating is, you know, this terminology of microevolution really means that something is adapting, right? It's changing. Well, cancer is one of those things that absolutely evolves. And it evolves within the organism in order to stay alive and survive. So it's quite fascinating to see how it does that. So if you follow this little diagram, and you think, we call it clonal proliferation, but it's really this idea of a cell evolving into something else. And it happens extremely fast. This does not take hundreds of years, thousands of years, right? In some patients, unfortunately, this happens within weeks to months. So this microevolution is actually very rapid within cancer biology. And it's a modern day example that demonstrates that within biological tissues and cells, we see evidence of this evolutionary process happening within medicine. All right, so here's a normal cell. Consider that this is maybe pancreatic cancer. Pancreatic cancer is extremely aggressive. Somebody's diagnosed with pancreatic cancer, usually it's like months before they're gone. Okay? Maybe a couple of years, but it doesn't have nearly the long-term outcome that breast cancer has, that we're sort of celebrating right now, Breast Cancer Awareness in this month. But pancreatic cancer would happen really, really fast. But all kind of cancers do this, and they happen really quickly. Even if you think about the fact that if somebody was a cancer-surviving patient for their entire life, they had this evolutionary process happening within their cells within a lifetime, within a 70-year period of time. We're not talking millennium here. So you got a normal cell, you get a induction of a mutagen. And now it becomes a tumor type cell. And this one's colored in red. And as it progresses and divides, it gets mutated again. It doesn't stop mutating. And it mutates into sort of this pink color. Well, this red color was favorable, so it sticks around. The pink one was favorable, it sticks around. And it mutates again into this purple variant. But the purple variant doesn't really help the tissue, so it dies off. And the pink variant continues on and develops into this sort of light teal blue, and that was beneficial. It continues on. This goes into this sort of sky blue. That continues on. So you even see here that there are certain variants that die off, or are selected against, if you want to use that terminology, right? And there are some that actually persist. So what you have at the end of this cancer development is you have these variants that have developed and mutated or evolved, microevolved. And you've got sort of the original red. The original red was a mutation that was metastatic. So you remember our little wheel diagram that we were going through with the little figures? This is sort of the output of what that wheel diagram looks like. Is we've got metastatic in red. We have requiring fewer growth factors sort of in this pink. We have non-antigenic in the sky blue. The mutation for invasive, meaning it goes into surrounding tissue because it increases its production maybe of matrix metalloproteases like collagenase, and it becomes more aggressive. All of these actually lead to this ultimate metastatic cancer. So how do we put everything together that we've been talking about today? This would be another tool that I would encourage you to use as a study tool. And everything that's on here we talked about today. We talked about each one of these boxes. And so if you can flow, for example, from a normal cell to DNA damage and successful repair, you could write over here P53 or retinoblastoma. Those would be tumor suppressor genes that you can write over the margin that generate the successful repair. Well, if you have the failure of DNA repair, and maybe that's a mutation or a proto-oncogene becoming oncogenic, right? That could be the example you write in the margin. And you can walk through all the different situations that we talked about today in each one of these boxes. If you can put explanations next to each box, you have a pretty good understanding or handle on this. This is kind of like a flowchart study guide for you. Okay? Look up here. Things that actually take it from normal to DNA damage. Chemicals, radiations, or viruses. Any of these that cause DNA damage can actually induce this mutagenic change. So here's a question for you. Kind of gearing up for the exam in a couple of weeks. Matrix metalloproteases. MMPs is the abbreviation. They're secreted by tumor cells and they're important for which feature of malignant tumors? Angiogenesis, anaplasia, invasiveness, apoptosis, or differentiation. I like invasiveness the best. I think we could write a A and C only option because angiogenesis does require some of those MMPs in order for the new blood element to grow out of the existing blood vessel. So if this is a test question and I had these, I think it would be a bad test question the way it's written. I think you could argue, so here's a great example of how you write bad test questions. I think you could argue A as being a valid response if that's the way you argue. So in the remaining time, let's talk a little bit about some of the incidences of cancer and some of the different types of causes. Obviously the causes we kind of walked around. We talked about environmental, like radiation, chemicals, but viruses can do that too, as well as inflammation. So the take-home message on this particular slide, again, this is from 2008, but actually a lot of the data is still really the same. For males, the number one is prostate cancer, okay? And for females, the number one is breast cancer, right? But you can kind of see how it breaks down between males and females, so that it should be no surprise that our big awareness is actually breast in females and prostate in men, okay? Pancreatic cancer is actually pretty small percentage, but it's extremely lethal. Carcinogens. What kind of carcinogens are out there? So, if we have a mutation that happens at the level of the germline versus the adult line, if it's at the germline, then it's a heritable trait. But if it's at the level of the adult line, then it's not heritable. It's still not infectious in either situation. We're talking about whether it can be passed on or whether it actually will just exist in that particular individual. But if we look at the list that can cause carcinogen activity. Chronic inflammation, like the example of Barrett to esophageal adenocarcinoma. Viral infections, bacterial infections as well, and even like ionizing radiation, environmental. We would put tobacco smoke and alcohol consumption under environmental. Okay? So how does each of these contribute to cancer as we kind of finish out our lecture today? Well, if you have a purulent inflammation in a tissue, like with ulcerative colitis, chronic untreated asthma, okay? So a lot of times patients that have asthma, not so much today, most of us are managed, but years ago, before there were a lot of common over-the-counter therapies, people would just kind of live with this long-term wheeze. And so we saw the incidence of the development of lung cancer was actually increased in chronic untreated asthmatics. Okay? So any type of smoldering inflammation, these inflammatory cells secrete cytokines. Those cytokines go into the tissue and recruit growth factors and recruit macrophages, right? And the macrophages come in and they create this reactive oxygen species. And if that chronic infection was to persist, you're going to get the rupture of some of those macrophages. That's going to cause damage to the tissue. That could cause alterations in the DNA. And that's how a chronic, untreated inflammatory event within a tissue can lead to a mutation in the DNA and cause a cancerous event to take place. Okay? So we see this happening with colon cancer. Within colon cancer patients, right, we see this sort of long-term irritation of the colon leading to an increase in the risk of colon cancer. So we'll see things like ulcerative colitis. We see certain types of disorders where the colon is inflamed, and those patients that are at higher risk of developing colon cancer. Are they going to? No, not always, but the risk goes up. Infections, viruses and bacteria. So here's a list for us to look at. The hepatitis virus causes damage to the liver and causes inflammation to happen within the liver, both B and C. That increases the risk of long-term liver cancer in patients that have chronic hepatitis symptoms. HPV, right? This is human papillomavirus. And there are patients that have HPV are at higher risk of developing cervical cancer. HIV patients, Kaposi sarcomas, and non-Hodgkin lymphomas are the uptick in the increased risk for these patients. The bacteria, the one that's most common leading to stomach cancer and duodenal cancer is this H. pylori. So this H. pylori, this is this Helicobacteria that gets into sort of the antrum and the pylorus region of the stomach and takes residence. This is an infection, a bacterial infection, that increases the risk of a peptidic ulcer from taking place, and that ulcer is a non-healing wound that's inflamed, and that can lead to a mutation in the DNA and cause stomach cancer. Okay? So cancer is not something that you can catch, but it is definitely something that we're at risk if we have long-term exposure to these things. So just in the closing time, I want to talk about radiation from the environment. So we've got UV radiation, right? We have things like asbestos and air pollution. We're now even seeing that there may be a tie between electromagnetic fields and an increase in DNA damage. The question mark exists on cell phones, right? Tobacco and alcohol for sure. Let's look at this slide, and then we're done. If we look at tobacco and alcohol, both of these can be mutagens. Here's alcohol consumption down on this axis. Here's our relative risk, and then tobacco smoking and cigarettes per day. We have over 30 different carcinogens found in cigarette smoke. Okay? And 30% of all cancer deaths seem to be attributed to tobacco. But what happens that we can see very quickly is if you combine sort of these mutagens together, and if you see alcohol consumption per day in grams per day, and you link that to cigarette smoke, the relative risk skyrockets in the category that you have the highest amount of both risk factors. So if you're on the lake smoking and drinking alcohol, you're really in bad shape of getting skin cancer, lung cancer, and liver cancer. Right? So combining these risks is one of the biggest problems within managing this patient population. So which of the following is not a typical characteristic of cancer cells? Loss of cellular destruct mechanisms, unlimited replication, autocrine stimulation, or decreased responsiveness to growth signals. D, they have an increased response to growth signals, right? Not a decrease. Okay. I'll be in my office hours this afternoon. Don't forget your quiz this Friday.